Combinatorial proof. So what is a combinatorial proof? It's one that proves a statement, right? Proves a theorem by counting a collection of objects, or maybe several collection of objects, but at least one collection of objects gets counted, and that's what makes it a combinatorial proof. This I want to say, now I'm biased because I'm a combinatorialist, but this many mathematicians would say that this is kind of the the 5-star gold standard of a proof, right? Of the best kind of proof. A lot of very, very often there are many proofs of the same result, right? And I would say on the spectrum of proofs, right? There's maybe at one extreme there would be something like an induction argument, and at the other extreme you'd have combinatorial proof, and in between you might have lots of other techniques, maybe something like a generating functions argument or other style of arguments. But in general, when you're doing proof, something like an induction argument is often seen as sort of the unsatisfying. And I don't mean unsatisfying in the sense that it's not rigorous or not valid, but unsatisfying in the sense that it doesn't lend any extra insight usually into the statement being proven. It verifies that it's true, an induction proof, beyond any shadow of any shadow of a doubt. You can bet your life savings on the truth of the result if you've done an induction proving it. So they're often sort of unsatisfying, but they typically are somewhat mechanical. Often an induction, I mean, there are tricky inductions out there, but often an induction is sort of, you set it up, you turn the crank, it works, right? It's somewhat algorithmic, the process of doing an induction proof in many, many, many cases. Whereas a combinatorial proof is usually very satisfying in sort of several aspects. On one hand, sometimes just aesthetically pleasing, right? It's very short, very elegant, very pretty. There isn't messy calculation typically involved, but and also satisfying in the sense that a combinatorial proof is likely to give you more insight, not just that, oh, now I know the statement's true, but now it's connected to some other objects in mathematics or maybe other branches of mathematics, because of it gives you more understanding, a deeper understanding of the results. So this is why it's seen to be a very, very desirable thing to find the combinatorial proof. People have gotten many papers of taking a result that was already known to be true, but that no one had found a nice combinatorial argument for it, and then they just find a nice combinatorial proof, and then that gets published, right? It's not a new result, but it's a new proof of a known result, right? This happens all the time in math journals. It's seen as a big accomplishment, right? So these are satisfying, very satisfying proofs, but they're rarely mechanical. They're often tricky. My coffee pot agrees, right? They're often tricky, that they require some sort of rabbit out of a hat. And the rabbit out of the hat is usually right here. What collection of objects do you count? Rarely is this collection of objects given to you up front. You might have to come up with the collection of objects on your own, and there isn't really a algorithm exactly for doing so, right? So that's what can make a combinatorial proof really tricky. What on earth collection of objects do you count to prove a desired statement, right? So let's look at some examples, right? Here is an example of a statement that you can prove by induction. And in fact, if you watch my induction video, I proved exactly this fact using induction, right? So let's prove the same statement again. I want to prove that the sum of consecutive 2 powers, right, that if you add up consecutive powers of 2, that it gives you 1 less than the next power of 2, right? This is a statement that, like I said, in my induction video, I proved exactly this statement. So it's, we already know this is true by induction, but I want to do this by a combinatorial proof, right? I don't want to do it by induction. I want to do a more elegant result, a more elegant argument for the same result, right? So now, like I said, sort of the rabbit out of the hat, a collection of objects. I claim we're going to do this by counting. By counting what? Well, this is where it just takes some some playing around. It helps if you've read lots of combinatorial proofs, you see frequently useful, oh, these kind of objects are often useful, right? So here's what I want to do in this case. Here's a way to interpret 2 to the n. So here's a hint, right? And where is this hint coming from? This is coming from this is a strategy that's used often in combinatorial proofs. So hint, let's interpret, if you have 2 to the k, let's interpret 2 to the k as bit strings, right, of k, zeros and ones, right? So 2 to the k, and I should say not just as strings, but as the number of, right, the number of bit strings of k, zeros and ones, right? So for example, to do a little sub example, right, if you had 2 to the 3, which is 8, right, that is the number of strings that we can assemble of 3 zeros and ones, right? Or sometimes, or you say binary strings. Sometimes the word binary gets used if it's just zeros and ones. So, and you could list them out, right? You could say, okay, 0, 0, 0, 0, 0, 1, 0, 1, 0, right? 0, 1, 1, 0, oops, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. There we go. There's 1, 2, 3, 4, 5, 6, 7, 8 strings of zeros and ones, strings of length 3, right? So there's 2 to the third. Note, why is this correct? Well, think of the number of ways to select k objects from n options, right? Now you have to think about, does order matter or not? Right here we have a bit string, so you can see the order, right? The order of, we're saying, say 1, 0, 1 is different than 1, 1, 0, right? So the order does matter, right? Where order matters, right? And can you have repeat selections? Yeah, look at this little list of 8 strings, right? 0 got selected multiple times in 0, 0, 0. We have 3 zeros, or 0, 0, 1, there are 2 zeros, right? So you can select 0 multiple times, or 1 got selected multiple times. If you couldn't do repeat selections by pigeonhole principle, right, you can't choose, the answer would be 0. You can't choose any strings from an alphabet of only 2 characters. You can't have strings of length 3 by with all distinct characters, right? By pigeonhole, you'd have, it's impossible, right? So but so here, the number of ways to select k objects from n options where order matters and repeats are allowed, right, is what? This is n raised to the k. This is one of our counting formulas from those 4 possibilities, whether order matters or not, repeats allowed or not. And in this case, the alphabet is 0 and 1, right? N equals 2 because you're choosing from this alphabet, right? The size of the set of options, 0 or 1, right, is 2. So so that's why 2 to the k is the number of binary strings with k digits. Right, so that's, I wanted to just sort of, explain that, because we're going to use this fact heavily. There are all these powers of 2 in this expression, in this identity that we want to prove. So having a combinatorial interpretation, right, of a power of 2 as counting something, in this case counting binary strings, this is going to help us come up with a combinatorial proof of this, right? So here's what I'm going to do. I'm going to now start to look at these terms and think, how can we get the left-hand side and the right-hand side to have the same interpretation, right? As counting the same collection of objects in two ways. So here's what I want to do. Let's start on the right-hand side, right? So let's say this, because just there's less going on the right-hand side. So let's start on the right-hand side. What could this be? This could be the number of binary strings of length n plus 1, right? That's the 2 to the n plus 1. But I'm subtracting 1 from it. So I need to throw away one string from this collection, right? So it's a little bit up to us. What string might we throw away? Well, I don't know. Maybe let's pick sort of a special string. What's a special string that we could throw away? Well, maybe the all zeros string, right? Without, right, the all zeros string, right? So if you want, you could say it's the number of non-zero, is maybe an easier way to say that. The number of non-zero binary strings of length n plus 1, right? That's one way you could describe this. So I'm going to say, okay, this is, I have n plus 1 digits here, right? And that's how many digits I have. And then, you could put ones and zeros however you like, right? You just can't have all zeros, right? That's the -1 on this right-hand side, as we toss that one element of this set. So now what I need to do is I need to somehow take this and make a correspondence, make a bijection, right? With, what is this? This is number of binary strings of length n, right? This is the number, in between we have a whole bunch more, right? I have length n minus 1. This is the number of binary strings of length 3, of length, binary strings of length 2, and so on, right? Length 1 and length 0. So this is the left-hand side of this expression versus the right-hand side. So somehow I want to get these to match, right? This is very often a useful place to look at a list, to list out some of your objects and just see if we can see this relationship between the two sets, right? So let's do this for a small value of n. Let's say let's do say n equals 4, because for n equals 4 it won't be totally ridiculous. It's only, right, it's only 16 strings, so it'll be big enough to show us what's going on. Or sorry, n equals 3, right? Let's try n equals 3. Let's try n equals 3. It won't be so large that we're here till the heat death of the universe trying to list out our objects, but it'll be large enough to hopefully get some insight. If you pick an n that's too small, there you won't have much written down and there's not much structure to see. So maybe 3 is a good middle ground between no insight on one hand and heat death of the universe on the other hand. So let's try. I love here, by the way, how I just implied that we're immortal. I guess if you're doing combinatorial proof, we transcended the limit confines of this flesh and blood, and you just live forever in pure consciousness and can think about these things. Except heat death of the universe. Apparently, even in this system, even the immortals can't escape that. All right, so returning to our mission here, let's try n equals 3. What do we have? We have, on one hand, let's look at the right hand side, right? So let's look at the 2 to the 3 plus 1 minus 1. This is our non-zero strings, right? Non-zero strings of length of length 4, right? That's what I'm looking at here. So there'll be 15 of these, right? 16 total with 0, they're all 0 string, but then 15 total, right? So what can I have here? Well, I can have 1, right? And then all zeros, or a 1 and 2 zeros and 1, and so on, right? What I'm doing here is I'm actually iterating through exactly this list up here where we listed out these 8 strings, right? I'm just iterating through that with a 1 in front. But then I can also iterate through that same list with a 0 out front, right? So I can do a 0 out front. Except this one I'm going to toss, right? Because it's all zeros. But then besides that one, then I can iterate through that same list with a 0 out front. Okay, there we go. So there I have this, this list, right? In kind of in 2 ways, right? So, or sorry, this list of 15 strings, right? All the non-zero strings of length 4, right? There were 16 total, and I crossed out the all 0 strings. So what do I want to do then? I want to connect this side, this right-hand side, with this left-hand side. Now, this left-hand side, I have smaller strings, right? So I want to say that somehow, my hope is that somehow this 2 to the 3 plus 1 minus 1 is made up of a 2 to the 3 plus a 2 to the 2 plus a 2 to the 1 plus a 1. So I'm going to look for, now, I mean, they're equal as numbers, right? It's saying that 15 equals 8 plus 4 plus 2 plus 1. That's true, right? Just by arithmetic. But I'd like to find kind of these. This is the goal, is to find these quantities on our list, but not just find them, anywhere, but find them in some sort of structural way, right? So here's what you could do. Let's look at, say 2 to the 3, right? This 2 to the 3. Well, hey, this 2 to the 3, look up here at these 8 strings, right? I already listed those out. I can find a copy of that in a certain sense on my list, right? I can find it right here, right? There's 8, 2 to the 3 items, and they're built in a very natural way. It's just this old list with a 1 tacked in front. That's nice. That's kind of nice, right? That seems like a correspondence between these larger strings and these smaller strings that's appearing in kind of a natural way, right? Okay, so well, that's sort of satisfying, right? I seem to have found this big part. There's one of the terms in my summations, right? All right, let's look now and let's see, can I repeat this, right? Can I find maybe, how about 2 to the 2? Where might I find this on this list? Well, I have, again, I want to look for, now what? Strings of length 4. Sorry, strings of length 2, right? So what list am I looking for? Here, I'm really looking for this list, 0, 0, 0, 1, 1, 0, 1, 1, right? That's what I'm looking for next. So I think I kind of see it, right? I see it, well, I kind of see it right there, right? That looks pretty good to me, right? And then can I find this? what is this? This is strings of length 1. So that's just 0 and 1. All right, well, I see that here, right? And then can I find this? This is, there's only one way to have a string of length 0, the empty string, right? Ah, cool. There's the empty string right there, right? The one remaining item left on my list. So this, now I'm actually seeing a correspondence, nice structural correspondence between the right-hand side and the left-hand side. On the right-hand side, I'm requiring that the string be non-zero. So there has to be at least a one in it somewhere, right? In the string. On the left-hand side, I'm not requiring that it's non-zero. I'm saying all strings, right? So here's what we could do. We could say, all right, to get from the strings on the left to the strings on the right, put a 1, right? Just record where's the first one that happens in the string, the longer string, right? For the orange block, the orange block corresponded to the first one being the first character, right? What about the blue block? The blue block is if the first one was the second character, and then you have 2 bits to fill in, right? The green block was if the first one was the third character, and then the purple block was if the first one was the fourth character. So it's saying, you have to have at least 1 because we said non-zero strings. So you put a 1 somewhere, right? Some number of zeros and then a 1, and then fill in the rest. We already had 1, so we don't care what happens after that. Fill in with any pile of zeros and 1s that you want. That's what's happening in this construction, right? So this is kind of seeing this construction for specifically for n equals 3. Once you see it here, it's not too bad to describe it in general. So this is the foundation. Once you see this connection in a finite case, then you can, well, they're all finite. And once you see this connection in this case of n equals 3, then you can describe it for a general n, right? So I would say now we're ready to write up our proof, right? So you could say, okay, here's what we're going to do is we're going to say, so let S be the set of non-zero binary strings of length n, and then we could say on one hand, this is the right hand side, right? On one hand, the size of S is 2 to the n, length n plus 1, to the n plus 1 minus 1, because what? Well, because we are selecting n plus 1 digits from 2 options, right? An alphabet of size 2, right? 0 or 1. So n plus 1 digits from 2 options, 0 or 1, where order matters and repeats aloud. Right. And so that gives us the 2 to the n plus 1, but then we discard the all zeros string. Right. So that's phase 1. That gets us the right hand side. Right. Now on the other, hand, what we could do is we can decompose this set. We can decompose S into a union, right? S1, S2, S3. And actually, in fact, I want starting at 0. That 0 is going to be empty, but just for uniformity, I want it there for reasons we'll see in a second. So decompose S into this union. And in fact, I'm going to use a more precise word than decompose, partition, right? This is really going to be a partition of S, meaning S equals this union of sets, but they're also disjoint, right? They're disjoint from each other. So I'm going to partition S into these subsets, and what these are going to be is where if you do S sub, say S sub j, right? If you have some S sub j, it's going to be the set is the set of all binary strings consisting of of what? Well, I want this to consist of strings of the form 0, 0, 0, 0, 0, 0, right? A bunch of zeros followed by a 1, and then followed by anything. Right? And I want the total length of this to be n plus 1, right? Because I'm trying to partition S, and that's what it is. That's what's in S is strings of length n plus 1, right? And what do I want here for the number on each side? Well, I want this on the left-hand side over here, right? I want to have j digits. Sorry, n plus 1 minus j digits, right? So then over here, we'll have any binary string of length j. So I'll have j digits over there, right? So this is me just describing in general what I wrote here in this example, right? So you're doing a certain number of zeros followed by a 1, and then fill in the remaining digits with any binary string based on how many digits you have left, right? So this will give us the set S sub j, right? Well, then I don't have any choices here, right? Here there's no choice at all. And here there are exactly 2 to the j choices, right? Or I shouldn't say no choice, but I should say just one choice, right? There's exactly one choice. I'm prescribing 0, 0, 0, 0, 0, 1. You have to pick exactly that for that prefix, but then the remainder of the string could be anything of the 2 to the j possible choices, right? So if by fundamental principle counting, right, there's one choice there times 2 to the j choices there. There are 2 to the j choices, right? 2 to the j ways to do this. So then what do I have? I then have, I know that S sub j equals exactly, the cardinality of S sub j is exactly 2 to the j, right? That's the number of ways I can do this. And then what do I know? Well, since these sets are disjoint, right, there's no inclusion exclusion on this union, right? These are disjoint sets. The intersections are all 0. So since the S sub j, S sub I are disjoint for, right, for distinct I and j, right, we have what? We have that the size of S would be the size of S0 plus the size of S1 plus the size of S2, and so on up to the size of Sn. So I know then that S is also, 1 plus 2 to the 1 plus 2 to the squared plus, and so on up to 2 to the n, right? So we've counted now the set S in 2 ways, right? Thus, we have what? On the one hand, we have that 2 to the n plus 1 minus 1 is the size of S. But on the other hand, we also have that this summation is the size of S. Right. This means that those two expressions are equal to each other because they're both equal to S, right? So the proof is done. Right, so there is a combinatorial proof of this fact, right? This fact that the sum of consecutive powers of 2 will always equal 1 less than the next power of 2. And maybe just to show it again, in a slightly larger, with a slightly larger n value, just one larger, so it doesn't get too big, right? So for example, n equals, let's look at n equals 4. If I wanted to see this argument again, what would I have here? I would have set S0, right, is just empty, right? Set S1, what does S1 have in it? S1 is going to have just a 0 or 1, right? Right, set S2 is going to have a 0, 0, 0, 1, a 1, 0, and a 1, 1 in it. Right, set S3 is going to have a 0, 0, 0, a 0, 0, 1, 0, 1, 0, 0, 1, 1, a 1, 0, 0, a 1, 0, 1, a 1, 1, 0, and 1, 1, 1. Right, that's what S3 will have in it, right? Except all of these, right? I want all of these to be subsets of S, of my big set S, right? And these aren't quite subsets of it because they're not the right length, right? So the strings aren't the right length, right? They're too short. So I'm gonna write out one more. I know it can be a bit tedious, right? Looking at these long lists of very similar looking objects, but it honestly, when you're doing combinatorics, it's hard to overstate the value of doing this, right? Of the intuition that you gain from doing some enumeration, right? And listing out some objects and really, really, really seeing in super concrete cases how these correspondences work, how these bijections work. This is really a bijection, right? We're making a correspondence between one list of objects and another. So there we go, there's S4, right? So now here's the thing is these really aren't the full sets S, right? I didn't write down the actual set here because think about, because remember, these are all, in truth, subsets of this set S. These need to be strings of length 5, right? And that one we actually don't need to move anything. But here's what we could do to get the strings of length 5, right? So we should be building non-zero strings of length 5, right? That's the elements, or that's the set S here, right? It's all strings, all non-zero strings of length 5 is our set S, right? S as it was defined up in this proof. So how do I do this? Well, S0 is all the things that you can pack onto 4 zeros followed by a 1, followed by nothing. That's why I have the empty symbol there. So I wrote empty there. You can think of it as the null string, meaning just don't put any characters on. So now it's a string of length 5, right? Here I'm going to put 1, 2, 3, 4 zeros and a 1 before everything, right? And that gives me, I'm going to put 3 zeros and a 1 before everything. And that gives me all the strings of length 5 that have a 1, their first one in the fourth digit. Right? This, which the null, you can get rid of the null if you want. Right? This is, these are all the strings of length 5 that have their first one in the 5th digit. These are all the strings of length 5 that have their first one in the 4th digit. Here we have all the strings of length 5 that have their first one in the 3rd digit. These are all the strings that have their first one in the 2nd digit. And these are all the strings of length 5 that have their first one in the 1st digit. There we go, right? We have a perfect partition. See, we took this set, this giant set, which is size 2 to the n plus 1 minus 1, and we partitioned it into subsets, right, that have size what? Size 1, size 2, size 2 squared, size 2 cubed, and size 2 to the 4th, right? Those are the sizes of the subsets that we partitioned it into. We did it by classifying elements by where does the first one occur? In what position does the first one occur? So that's, here, it maybe looks really abstract when you look at it this way, right? When you look at this description of it. But what we're doing is really something extremely concrete, right? When you actually write out the bit strings and then write out the partition that we found, right? So this is a really common strategy. If you have a summation, right, try to count, the total for it, and then try to represent the terms in the sum, try to represent those as sizes of parts in a partition, but not just a random partition, but a partition with structure, one with generalizable structure, one that you can describe that structure for any n, right? So this is the whole collection, right? And I'm mentioning this because this is a really common strategy for doing combinatorial proofs of summation identities, different identities, maybe different strategy. So this is a whole collection. This is the sizes of parts in a partition. So there we go. There's a combinatorial proof. And of course, the combinatorial proof, it was done up here. Proof to end of proof, right? Box, Halmos, tombstone symbol. But I just wanted to sort of illustrate this in a little bit bigger example to really see what this partition is for n equals 4, right? For a little bit larger value. So great. So there we go. Proof, combinatorial proof. Do we learn something new in the sense of, have we proven a new theorem we didn't have before? No, we already knew this was true, right? We already knew this was true by induction. We did that in the previous video. But there's a whole lot more structure now when you see this identity, and you can think of these bit strings and decomposing them into different strings of different types. There's a lot more structure there than the induction proof, which doesn't put any extra structure in your mind, right? It just tells you that it's true. So this is where you have to work a lot harder for this proof, right? There's a lot more going on, but there's quite a bit to be gained from it, right? As opposed to this one where it's, it works, but it's sort of, it's just sort of, okay, we did it, right? it works, right? Yeah, but so hopefully you see the aesthetics here, right? How different a combinatorial proof is versus an induction proof. If this seems confusing, hang in there. Read tons of more examples of lots of more combinatorial proofs, and they'll start to feel more natural. They never get easy. It's still difficult when you meet a new one, but they're very attractive. They're very aesthetically pleasing proofs. So great, thanks so much.